So for waiting time type of problems, they're actually called geometric distribution. Okay, so the conditions for the geometric distribution are the same as binomial. Conditions for geometric are the same as binomial. Okay? So, and those conditions are, let me write them here. 1, repeated trials. 2, independent trials. 3, 2 outcomes. Just like binomial, right? So the repeated identical trials, they're independent trials. The probabilities do not change from trial to trial. And there are 2 outcomes, success or failure. Yes. The difference is in the type of question. Difference is in the, is in the question being asked. Okay. And the question being asked is a waiting time question. So, what is the for example, what is the probability that you can roll a sum of 7 on a pair of dice in fewer than 3 rolls? Okay? If traffic flows at a given rate, what is the expected length of time that a pedestrian must wait before crossing the street? So it's a waiting time question. Binomial asks, well, if you roll a die 5 times, what's the probability you'll get a 2 3 times? Right? It just asks a probability question. This again, we're calculating probability, but we're calculating the probability basically of how long something will take. Okay? Okay. Again, it's identical, it's independent, success or failure outcomes. We want the number of trials prior to the first success is called the waiting period before success. Okay? And the random variable x is the number of trials before a success. Okay? Note that before a success. Emphasis on before. The probability distribution is given by the geometric distribution. The probability x equals any value is the probability of failure to the exponent x times the probability of success. And expected waiting time is Q over P. So I'm going to explain all of that as we go through the examples, okay? Here's example 1. In repeated rolling of a pair of dice, what is the probability that the first roll of doubles occurs on the third roll? Okay, so let's take a look at that. Well, let's just say D equals doubles. Okay. D is for doubles. D naught is for not doubles. Notice success or failure. The probability of success is, the probability of doubles is 6 out of 36 or 1 over 6. And the probability of failure is 5 over 6. Does anyone need me to explain how we get that? Okay. Now, x equals 2. It's the waiting time. The first roll of doubles occurs on the third row. So on the first row, you do not get doubles, right? On the second row, you do not get doubles. So our waiting time is 2, and we get doubles by the third row. So let x be the number of trials before a success. So the probability x equals 2 is equal to the probability of failure squared, right? Probability of failure times the probability of success. So it's going to be probability of failure is 5 over 6 squared times probability of success is 1 over 6, and that is equal to 25 over 216. So the probability of having to wait 2 rolls before you get your doubles is 25 over 216. Let's look at part B. What is the expected value of x? Well, that's q over p. That's 5 over 6 over 1 over 6. We divide by a fraction, we multiply by the reciprocal. So that equals 5. On average, you can expect to roll 5 times before getting a double. Okay. In a gambling game, a player tosses a coin until a head is uppermost. He then receives $2 times n, where n is the number of tosses. So I guess the longer it takes to get ahead, the more money he can get. What is the probability that the player receives $8 in one play of the game? Okay. So he's making $2 a toss. To win $8, in order to win $8, he must toss 4 times. Right? Because 4 times 2 is equal to 8. So that means he must, if he tosses 4 times, then he must get a tail, a tail, a tail, then a head. Because once he gets a head, he stops tossing. So we want, our waiting time is 3. Probability x equals 3 is equal to probability of a tail is to the 3, probability of a head to the 1, and that equals 1 over 16. player must pay $5. What is his win-loss per game? Okay, so whenever you're talking about win-loss, is the game fair, etc., we're looking at expected value. So the expected win the expected waiting time to get ahead is equal to probability of failure divided by probability of success, and that's 1/2 divided by 1/2, and that equals 1. So on average, there are 2 tosses, right? Because if your expected waiting time is 1, you're going to get a tail before you get a head. On average, there are 2 tosses. The loss per game is the loss per game. Well, he gets $2 per toss, right? So $2 times 2 tosses minus $5 to play is equal to minus $1. So the expected loss per game, the expected loss per game is $1. Number 3. What is the probability of rolling a sum of 7 in fewer than 3 rolls of a pair of dice? Well, let's just look at this. You could get a sum of 7 on the first roll, or on the second roll, or on the third roll. Is this fewer than 3 rolls? So if I look at that, that's 1 roll, that's 2 rolls, this is 3 rolls. Is that fewer than 3 rolls? No. So this one is no good. We cross that one out. So we want, okay, we'll say let x be the number of rolls before getting a sum of 7. So we want the probability x is less than or equal to 1, right? Right, because here the waiting time is 0, here the waiting time is 2, but here the waiting time is 1, right? So it's less than or equal to 1. That's the probability of 0 plus the probability of 1, and this one we don't count because that's not fewer than 3 rolls. So that will equal probability of success, right? Probability of rolling a sum of 7 is 1 over 6. Probability of failure is 5 over 6. So we're going to have 0 failures, 5 over 6 to the 0 times 1 over 7 plus 5 over 6 to the 1, right? Our waiting time of 1 times 1 over 7. And that is equal to 11 over 36. Yeah. Huh? Yeah, my bad. Thank you so much. You're absolutely right. I was thinking sum of 7 and the answer's right. Can I explain anything better? I would just ask that you put your cell phones away. Okay, at a certain corner, you need 10 seconds on average to cross the street. If during 70% of the 10-second intervals there's traffic on the street, how long will you expect to wait to cross? Okay, so success is when there is no traffic on the street. Okay, so on a certain corner, you need 10 seconds on average to cross the street. 70% of the 10-second intervals, there is traffic on the street. So that means the probability of success is 0.3. The probability of failure is 0.7, right? Because 70% there is traffic, 30% there's no traffic. So that's our probability of success. The expected value of x is equal to Q over P, and that's 0.7 over 0.3. That's 7 over 3, which is about 2.3. So on average, you can expect to wait 2.3 intervals of 10 seconds each. Or 23 seconds. Yes. Oh, you're okay? Okay. I was going to put it in my calculator. Any other questions?